Okay, so again, the notes are going to do a little bit of review of that reading guide, but then we're going to take it a step further as well. So this first slide are things that we went over on the reading guide. So if you already have them down in the reading guide and you're comfortable with that, great. If you want to jot them down, you can. Again, starting with the first bullet point, acids are fairly common in foods. Not all foods, but they're in a fair amount. Bless you. Now, conduct electricity. We've probably heard of the term battery acid before. One of the acids for battery acid, especially if it's a car battery, for example, is sulfuric acid. Sulfuric acid is an acid that we will be working with in the lab on Monday. Not every battery acid is actually an acid. Again, you just need something to conduct electricity. But acids are good at that because acids will have ions in solution. And we'll show you that in a little bit. Usually, you don't have an acid that's a solid, although some of them can be that you then dissolve into water, make a solution. Usually we have more solution or liquid phase acids, but they can be in the gas phase as well. So you could actually breathe that in, which would be harmful. Again, the fourth bullet point is one that I mentioned with the reading guide that we already saw in the lab. Acids will react with metals in a single displacement type reaction. And in doing so, they create hydrogen gas and then some other product as well. And the last thing on this bullet point or on this slide is that acids have a pH below 7. Now the pH scale itself, I'm hoping to talk about either later today or at the beginning of next class period, just depends on how long everything takes. But these are just some general characteristics. I would caution you that my next slide is going to go over kind of what defines it as an acid. A pH below 7 does not define something as an acid. And the reason why it gets a little bit tricky, because it's something we have to go over more in AP chemistry, I just want to make sure that we're aware of these are more just general characteristics, not specific definitions of what makes it that way. Because the pH scale is a little bit more complicated than we get into. Again, we cover a lot. Actually, in AP chemistry, we just got done with our acid unit. And it is significantly different than what we cover in Chem 1. Because our goals in Chem 1 are that you know what is an acid and what is a base. So what makes something an acid? What makes something a base? What happens when you mix an acid and a base together? They neutralize. So how do we write that reaction? And we can even do a little bit of stoichiometry with that as well, which we will go over on Monday. But really, those are our main goals for acids and bases, is know a little bit about each, know how that pH scale works, know what happens when you mix the two. So there's a lot more that goes into acid-base chemistry that we're not going to get into. Now, there's actually 3 definitions of acids out there because over time our knowledge of the subject increases, so then we're able to get a better and better definition. However, the third definition we do not cover in Chem 1 because it is a little bit more confusing. So we stick with the 2 simplest definitions. The original definition of an acid, brought to you by someone named Arrhenius, is when you put an acid in water, so in a solution, it creates what's called the H3O plus ion. That H3O plus ion that I have on that first dash is referred to as the hydronium ion. So that's a bit of vocabulary that you should be familiar with. Hydronium is H3O plus. The second definition of what makes something an acid, it eliminates the fact that water has to be involved. So no longer does it have to be in a solution. An acid is just anything that can donate an H+. And by the way, we will often refer to H+ as a proton. Because if you think about it, H stands for hydrogen. Hydrogen's nucleus has 1 proton, and around it has 1 electron. But if it loses that 1 electron to become a positive charge, it's now just really a proton. What I'd like to do is, once you jot this down, I'm going to kind of draw out an example to explain how both these definitions can be used to explain how something is an acid. The most common acid that high school chemistry students work with is hydrochloric acid, HCl. Okay? So, I'm going to draw out the Lewis dot of HCl. Chlorine, partial negative, hydrogen, partial positive. Remember polarity? Now, if hydrochloric acid was placed in water, so I'm going to draw water. Water, you betcha it's a polar molecule. Notice how I drew it. My oxygen on water is a partial negative. I have it next to the hydrogen on hydrochloric acid, which is a partial positive. And actually, this is such a great attraction that what can happen is these electrons will form a bond. So they attract, and water steals a hydrogen away. Or hydrochloric acid gives an H away. If that bond happens, this bond has to break. Because what happens when you put hydrochloric acid in water is the H part in HCl goes to water. And that makes that hydronium ion. So this donates an H plus to this. The leftover then would be a Cl minus. Again, if I drew the Lewis dot of that when everything was done, my chlorine would now have 8 electrons around to be a negative charge. My water gained another hydrogen. Things can conduct electricity if they have ions in solution. I mean, salt water can conduct electricity. So why acids can conduct electricity is based upon this reaction I have up there on the board. When this bond breaks right here between the H and the Cl, remember a bond is 2 electrons. So those 2 electrons get deposited around the chlorine. So now it's the chloride ion. That's another reason why it's called the H plus, that neither of these electrons in that bond belong to the hydrogen really when it gets donated. So if I remind you of what that previous PowerPoint slide said, is an acid is something that can donate a hydrogen in water to make this hydronium ion, this H3O plus. An acid is something that could just donate a hydrogen to anything though, really. And HCl can get rid of that hydrogen, that H plus. Okay, so I wanted to give you in PowerPoint the word form. I wanted to kind of draw it out for you a little bit as well. But this is explaining what makes some things an acid, because not everything that contains a hydrogen will lose that hydrogen. I mean, part of it deals with polarity, like I showed in that Lewis dot there. If there's not an attraction between water and that hydrogen, it's hard for that hydrogen to be lost. And if it can't be lost, it's not donating a hydrogen. It's not really an acid then. So there's plenty of things out there that have hydrogen bonded to them, but they're not an acid. Get this out of the way. Okay. There are a lot of acids out there. And there is actually naming rules dealing with that as well. Instead of teaching you 3 new rules of naming, we ask that you know 4 acids. I'd have to look back at our unit test, but in years past, we've told students they need to memorize these 4 acids because these are the 4 most common acids that they are going to be working with. Hydrochloric acid was my second one I have on this list. That's what I showed you on that last drawing. HCl. Nitric acid and sulfuric acid and acetic acid are the other 3. Now, what might help you out in remembering those other 3? Sulfuric acid has the sulfate polyatomic ion in its formula. And you guys always get to use your polyatomic ion sheet. And why is it H2SO4? Well, sulfate polyatomic ion is a -2 charge. 2 hydrogens balance it out. Referring back to the reading guide, it's what we call a diprotic acid. It can donate 2 hydrogens because it has 2 in its formula. Nitric acid has the nitrate polyatomic ion in it. And since the nitrate polyatomic ion is a -1 charge, there's only 1 hydrogen that goes with that. Nitric acid is one of the acids that we're going to be using for the chemistry semester project. Acetic acid has the acetate polyatomic ion, C2H3O2. Acetate polyatomic ion is a -1 charge. There's only 1 hydrogen with it. So if you have your polyatomic ion sheet, that might help you remember these as well. Now, acetic acid isn't one that we specifically use in the lab. However, it's one that we have in a classroom for safety purposes. Acetic acid is one of the main ingredients in vinegar. We keep vinegar in all the chemistry classrooms because it can help neutralize some spills. So we actually won't be using acetic acid in the laboratory, but you might have to use it if you have a spill of a certain thing, you have to neutralize it. Because in this unit, if we spill something, we don't just wipe it up with a paper towel. Soaks up in the paper towel, gets on your hand, now you could have acid on your hand. That's not good for you. We don't just wipe it up with water either, because sometimes diluting with water is not enough. We need to neutralize it. So that's why we have the vinegar, the acetic acid in the room. So we ask that you be aware of these. And then I have a question of what do they have all in common? Well, what do acids all have in common? They start with a hydrogen. It's important to note it's the hydrogen that they start with that makes them an acid. Because look at acetic acid. Acetic acid actually has 4 hydrogens in its formula. But it would only donate 1. That's why we don't actually call this C2H4O2. We don't put it all together. Because I understand simplifying it, why don't we just call the hydrogens together, makes sense a certain amount. To indicate that it's an acid, it leads with a hydrogen. And only those leading hydrogens are the ones that can be donated. So acetic acid cannot donate 4 hydrogens, even though there are 4 in its formula. Okay, so most people, when they hear the term acids, they're like, ooh, that's dangerous. We have to be careful, which is true. But every bit as dangerous, just on the opposite end of the pH scale, are bases. So I do the same sort of slides that I did with the acids, some general characteristics of bases. Very common to find a base to start as a solid. So acids, usually not that way. Bases, very common that way. However, bases, we will often dissolve in water. That's why they'll be a solution. That's why I say they can be aqueous. In some cleaning products, you get them on your hand and your fingers just seem to glide in between the two. Because bases are slippery. And boy, oh boy, my third bullet point. I keep on referencing a movie from the mid-90s with Brad Pitt called Fight Club, where he takes a base and he mixes it with oils to make a soap, and that's what he does for a living. However, he also takes that base and sometimes it gets put on like people's hands and they get a chemical burn. because the movie Fight Club is a fairly violent movie. It's about people that try to beat each other up for fun. They're not angry at each other, it's just what they do to release stress. But then it takes a turn at some point. But I referenced the movie because it reminds me that, to remind you guys that bases are every bit as dangerous as acids. The movie shows people getting chemical burns from that base once in a while. However, if you mix it with the right thing, you mix it with oils, it's soap that we all use, hopefully. Last two bullet points again, bases conduct electricity. I'll show you that just like acids do. And actually some batteries are composed of bases, not of acids, even though the term is always battery acid. That's not always the case. And once again, the pH scale will show that bases are typically above 7 on that pH scale. Okay, we ready? So, just like acids had more than one definition, acid-base chemistry, again, developed our knowledge over time. The first definition of a base was that it would put OH minus, hydroxide polyatomic ion, in a solution. So this actually matches up with the Arrhenius definition of an acid of creating hydronium. Second definition is a base is anything that accepts a proton. Remember, an acid donates a proton. An acid will give an H plus to something else. Well, a base can accept an H plus. And once again, when you have this written down, I'm going to go back to drawing out an example of this to show these two definitions in action. Ready? So, a very common base that you might have with your cleaning supplies at home is ammonia. Ammonia is NH3. If I draw out the Lewis dot of it, looks like this. The nitrogen is the partial negative end. The hydrogens are the partial positive. Remember, it's a polar molecule. There's an unequal sharing of electrons because nitrogen is more electronegative. It has a greater pull on those bonds. If ammonia is dissolved in water to make a solution, what will happen is the partial negative end of ammonia will attract the partial positive of water. And those two electrons that I circled will create a bond with that hydrogen. Kind of like how the HCl lost its hydrogen. Well, the NH3 is going to gain a hydrogen, which means this bond right here is going to break. In essence, in this chemical reaction I have up here, NH3 is going to gain an H+, turning into NH4+, which is the ammonium polyatomic ion. It is the positive polyatomic ion on your polyatomic ion sheet. And that H+ that made it go from ammonia to ammonium was donated by the water, which leaves water as OH minus. I draw out the Lewis dot of our remaining products. Ammonia is a +1 charge. hydroxide is a minus 1 charge. So the two definitions I gave you of a base, one is it creates hydroxide when it's in water. This is an example of that. Second definition of a base is it is something that will accept a proton. Acids give it, bases can accept it. NH3 is accepting an H from the water. You know what's kind of unusual about these two slides I have right here? In one example, water is taking the H+. Another example, water is giving the H+. Whatever water is around determines how water will behave. So in one example, water is actually going to take that H+ away. It's acting kind of like a base. In this example, it's going to give that H+. It's acting almost like an acid. But water is in the middle. It's neutral for a reason, because it can do a little bit of both depending upon what it's around. Okay, a couple more slides to go. Now, I don't think you have to write down the common bases, because these are all examples of naming that you should already be aware of. Sodium hydroxide, calcium hydroxide, calcium carbonate, metal with a non-metal polyatomic ion each time. Ammonia is the only one that I drew up on the board that doesn't follow the naming pattern for ionic compounds that we've already done. And then the question I remind myself to give everyone is looking at the formulas of some common bases. What do you notice that the first two have in common? They end with OH, hydroxide. Just being able to look at a formula and recognize, is it an acid or is it a base, I think is a good thing to be aware of. Which, when I mentioned how water can act kind of like an acid or as a base, remember the formula of water is H2O. Or we could write it as HOH. It has a hydrogen in the front, it could donate. It has a hydroxide at the end. But since it has both, it balances each other out. And to neutralize means to balance out the acid and the base particles. And that's what our last slide is going to go over, is what happens when we mix an acid and a base together. So again, these bases up on the board, really not a matter of memorization, because you always get to use your periodic table and polyatomic ion sheet, so you should be able to figure out the formulas. The acids you have to think about a little bit. Use your polyatomic ion sheet, add some hydrogens to them to get the charges balanced out. Okay, so what we're going to end with is there's two different types of neutralization reactions that we're going to have you practice writing here in a few minutes. So I'm going to go over one more slide with a couple examples, and then you guys are going to start working on your own with each other, however it might be. There are two different types of neutralization reactions that we want to go over. The first is the simplest version. Let's say acetic acid plus barium hydroxide. If we were doing a laboratory experiment with barium hydroxide and we spilled it on the lab bench, bases are dangerous. Don't just wipe them up with a paper towel that'll soak through the paper towel and onto your hand. Instead, we try to neutralize the spill. So if we spill a base on a lab bench, we're going to pour vinegar on top of it, because vinegar contains acetic acid. And then we'll just wipe it up, because once we neutralize it, it's no longer as dangerous. So what I'm going to do is I'm going to switch back over, and I'm going to write this equation for you. So you see, like, the reactants in word form, similar to the test that you just took. We could give you just the reactants in word form. You have to write out the rest of the reaction. Acetic acid's formula is HC2H3O2. And our acids are going to be a solution, so I'm going to call it aqueous. Barium hydroxide was not one of them on my list on that previous slide. However, anything that ends in hydroxide, hopefully bells are going off in your head of, hey, this is a base. Well, that's a parentheses and then a 2. And again, bases could be a pure solid or they're going to be a solution. If it helps, although it's not necessary, I could put parentheses around my acetate polyatomic ion. Here's the good news about this type of reaction. My hope is by looking at the reactants, this looks a little familiar. You were taught 5 reaction types last unit. Which reaction type does this remind you of, where I have 2 solutions? Synthesis? No. Double displacement. And in double displacement, the cations trade places. No different here. That's what's going to happen right now. I'm sorry I'm running out of room a little bit, so I'm going to write my products kind of below. Barium is now going to match up with the acetate polyatomic ion. However, just like in last unit, when you make the switch, you have to rebalance formulas. And what I mean by that is barium is a +2 charge, acetate is a -1 charge. So my formula for barium acetate would be Ba parentheses C2H3O2 2. And I mean, you can look on your solubility table to see, is it going to be a solid or aqueous? I believe this is going to be aqueous. And sorry for writing sideways, I'm just running out of room. The other product, hydrogen, is going to match up with hydroxide. There's 2 ways that you could write this. You could either write it as hydrogen hydroxide, because hydrogen's a +1, hydroxide's a -1. That's how they balance out, so that 2. Or we could just write that out as water. They mean the same thing. The one advantage, perhaps, to writing it out as HOH is we still didn't balance our equation. Notice how I have 2 acetates on this side of the equation, my product side. I would need to put a big 2 in front of my acetic acid to balance that out. Now I have 2 hydrogens here. I only have 1 hydrogen on my product side. I have 2 hydroxides on the reactant side. I only have 1 here. I need a 2 in front of that to balance this out. Or I could have called it 2H2O. So sometimes to help balance the equation, students will write water as HOH. But a neutralization reaction between an acid and base is going to make water. Phase notation for water, it's a liquid. When we taught you double displacement, we said you had to make a solid, a precipitate. Remember using the solubility table? Technically, you have to make something that isn't aqueous. So making a pure liquid like water, a pure gas, would also mean that reaction occurs. So this is the simple type of neutralization reaction. And when you think neutralization reaction, you should know one product right away: water. Water is neutral for us. So that's the first product you should be thinking of. The second one is some sort of ionic compound, metal and nonmetal. Okay, last one, and then we are done with this round here. I gave you that first example because if we spilled a base in the classroom, we'd pour vinegar on it to keep that neutralized so we can clean it up. Well, what if we spill an acid? If we spill an acid, we would use a carbonate base instead. Now, we have baking soda that we use, which is sodium bicarbonate. I'm going to give you a different example of calcium carbonate. Calcium carbonate is one of the main components in limestone, a bedrock. also in chalk. It's also in bones. Nitric acid is one of the acids that we're going to be using in the semester project. But also, nitric acid is one of the, let's call it, ingredients in acid rain. So if you've heard of acid rain before, pollutants in the air get dissolved by water because water is so good at dissolving things, and it turns it into nitric acid. Nitric acid can come raining down in things. If you have a marble statue, marble, one of the main components of it is calcium carbonate. Marble statues over time will break down if they're in the presence of acid rain because it will react with it. So I'm going to show you that reaction to finish this up. So nitric acid was HNO3, and our acids are always going to be a solution aqueous. Calcium carbonate, however, is a solid. Again, limestone, marble, chalk, bone. What makes calcium carbonate different is it's not a base that ends in hydroxide. Still looks like double displacement to me, though, or this switch is going to happen. So, my first product would be calcium with nitrate. Calcium's a +2, nitrate's a -1. Calcium nitrate would be one product. Now here's where this one is a little bit trickier. That means hydrogen needs to pair up with the carbonate. Hydrogen +1, carbonate -2. So originally, I would say to myself that the other product would be H2CO3. However, that H2CO3 almost decomposes on its own. This is an acid-base reaction. Besides an ionic compound, what is always made in an acid-base or neutralization reaction? Water. That water is in here. H2, and there's at least one O in here. So, this H2CO3, again, that H2CO3 actually is going to break down. And it makes water, which is a pure liquid. And if you take the H2O out of H2CO3, you're left with one other compound, CO2. In the double displacement lab, you created a precipitate. You put it in the centrifuge, but spun it really fast, and then you added acid to that precipitate that was made with a carbonate. And you saw bubbles. You saw carbon dioxide. You spill an acid on the lab bench and you get baking soda and pour it on top, and you're like, Mr. Rotzenberg, I don't know, did I put enough acid, baking soda on it? Is it neutralized? Well, if it's still bubbling, there must be still acid present. But once it's done bubbling, we ran out of acid to make that carbon dioxide. So there's two types of acid-based reactions we need to be aware of. Your simplest one is going to make water and an ionic compound. Typically, that's a base that ends in hydroxide. The second one is going to be a base that ends in carbonate, is actually going to make three products. The ionic compound, the water, and the carbon dioxide. What we're going to have you do right now is, besides the retake sheet you picked up on the way in, if you wanted to do that for a review, you picked up a sheet on the way in that's going to give you practice in writing reactions. Again, feel free to move about and start working on this, and I'll come around if you need help.